Next one. This is a big one. Unknown attribute values. There are a couple of respects in which everything that we've been doing so far is very unrealistic. The first one is we've assumed that you have all attributes for all examples. The second one has to do with noise, and we're going to spend a large chunk of the second half of this class on it. Okay? But let's just look at this one for now. Most of the time, you do not know all the values of all the attributes. Like, for example, you're doing medical diagnosis and you have a battery of 1,000 tests that you could do on a patient. But God forbid that you have inflicted all of these 10,000, all these 1,000 tests on each one of the patients. Probably only have some of them. Different for different patients because different ones are relevant, but for most of them you're missing the information. And this is even a case where there's some, they're actually not missing at random. You could actually have values that are just completely missing at random. You just don't know the values of some things for some people. And then what do? Right? The algorithm that we have so far always assumes that I'm able to evaluate every attribute at every point because I know its value for all the examples in the data set. And most of the time that does not happen. And again, Murphy's law of data mining is that the bigger the data set, the crappier it is. So on a small data set that somebody painstakingly gathered of 1,000 examples, well, sure, maybe you have all the values. On a very large thing, you probably don't. For example, this is a very typical example. On the clickstream data, you actually have three kinds of data. You have the actual clickstream of the person. They clicked on this and then they clicked on that. This they have for everybody because the server is gathering this at every moment. And then for some people, but only a small subset, they actually filled out a registration form for the site. So you know a lot about them because they actually took the trouble of filling that out. Precious information, but you only have that for a fraction of the people. And then there's another fraction of the people that you somehow got some demographic data on from one of these companies that sell it. Okay? And that can also be very useful, but again, that's only a small fraction of the people. The people for whom you have all these things, you have the clickstream and you have the registration information, you have the demographic information, is a small subset. You don't want to ignore the information, the demographic and the registration information for the people that you do have it for, right? But at the same time, you have to know what to do with the people that you don't have that for. Okay? So how might you handle that, right? What would you do, right? If you had just built your decision tree learner and you were 5 minutes from the project due date, right? It was due 5 minutes later, and you needed to come up with a method to handle missing data. What would you do?
Prioritize and update the route to direct them towards where the information came.
Okay, so let's look, for example, at the root, right? We're at the root and we're trying to pick an attribute for the root, right? And let's say for some of these attributes, I do have the value. For some of these examples, I have the value of the attribute. For some of these attributes, I have the value for all the examples. Right? So for those, I'm okay. But now there are some examples for which I don't know some of the attributes. Right? So now I'm looking at an example. I'm trying to evaluate, attribute A. Like, say, the color. Right? For some of these people, I don't know the color of the car that they last bought. Right? So what do?
Compute on other variables?
Yeah, impute it, right? Right? This is actually the statistical term is imputed. Imputed meaning, like saying, I'm going to make up a value for it. Right? Make up a value. It doesn't have a value, well, darn it, I'll force it to have a value, because that way I can keep going. Okay? So if you're going to impute a value, what value should you impute?
Most common one.
The most common one, right? So 80% of the people bought black cars, 10% white, and 10% red, right? Well, in the absence of that information, if I'm going to have to pretend that I know the color of this car, I'm going to pretend, that it's black. Okay? So this is indeed the first strategy. It's quick. It's better than nothing. But there's another strategy that is almost as quick and is way better. Any guesses what that might be? Here's a hint. Remember, why am I doing this? I'm looking at these attribute values because I want to predict the class. Right? This is the purpose of the exercise, is to come out with the class prediction at the end of the day. Right? So what I really want to do is I want to judge whether you're going to want to buy this car or not, depending on its color. Right? So how might I incorporate the class into this process? Remember, this example, right, I'm not trying to decide which way in the tree this example goes, right, if I split on this attribute. And I do know the class for this example. I do know whether you bought the car or not. Okay? So What can I do?
Look at other examples that have the same class.
Yep, exactly. So that is strategy number 2. I assign the most common value among examples of the same class. Because that's what I care about. Of the cars that I bought, how many were black? Or that the customers bought, right? How many of them weren't? Right? Among all the products in this catalog, right, I have a lot of, probably not a car, but let's say I had a product, right? I have a lot of that information. I'm trying to correlate things with the class, so I shouldn't throw the class away when I'm imputing the value of this attribute. This is barely any more work than the previous strategy, but it often works way better, so, I would recommend that. However, you can do even better. Here's what you can do that's even better. You don't know what the value of this attribute is, right? But if you think about it, when you just impute one value, you're doing something that's probably quite unrealistic. You know that in reality, these people didn't all want to buy a black car. Some of them wanted the red one. Okay? So what you can do is, instead of imputing it all the way, what you can do is you can impute fractionally. You say, if among the people who did buy, 80%, the color was black, 10% was red, 10% was white. What I'm going to do is I'm going to split this example into 3. One example with a weight of 0.8, so it counts as 0.8 of an example. I'm going to say this is an example where you bought the car and it was black. And I'm going to have 0.1 of an example where the color was red and 0.1 of an example where the color was white. Okay? So now the example becomes 3 fractional examples. Think of this as dividing the cake, right? You don't send the whole cake down one branch. You divide it into pieces proportional to the real empirical probabilities, and then you divide it that way. And if then you come up another, a missing value, right? Then you do the same thing again. You split the cake further into smaller and smaller crumbs. And everything that we've been doing in terms of computing entropies and errors and whatnot, it works just as well with fraction examples as with whole examples, so there's no problem there. Okay? Questions about this? So this is at learning time, right? So this is what I use, and I'm able to compute all my information gains, I'm happy, right? But now what happens at classification time, right? Before, when we had no missing data, right? I had my example with its attributes. When I came to the next node, I always had, the value of the example, so I knew how to route the example, right? But now let's say I have my decision tree, and I'm not trying to classify this new car, and now I come upon color, and I don't know the color, right? So what do I do? I can do the same thing that I did at training time, right? Which is I can break up the car into 0.8 and 0.1 and 0.1 and send it down 3 branches, right? And then they all trickle, and then they keep splitting, and then they all trickle down to the leaves, right? Not a problem there. It's the same thing at training and at test time. But the problem now is, so now what do I predict, right? In the complete data scenario, each example at test time always went down to exactly 1 leaf, and so I predicted the class at that leaf. Now an example basically just rains down on a whole bunch of leaves, right? So now which class do I predict? Any suggestions?
The one with the highest weightage kind of get.
Yeah, the highest weighted, that's the answer, right? The answer is democracy, right? Let them vote, right? Which leaf picked up the most breadcrumbs? Right? Or the biggest, some were small, some were low, right? So you have a little scale at each leaf and you weigh the total amount of cake that fell there, and whichever leaf has the biggest weight of cake wins, right? This is the first of many instances where voting is a great thing to do in machine learning, right? Whenever you're trying to handle, things that you're not sure what to do, one good idea is always like, well, let them vote, right? Let the crowd make the decision, right? This is like, crowdsourcing, right? The wisdom of crowds, except in this case, it's the wisdom of the algorithms, but the principle is the same. In fact, we'll have a whole class, as I mentioned, last time, about how to, combine models, and you could see this as a very simple example of that. Okay. In fact, in an interesting twist, people initially developed the ability to handle fractional examples because of this, because of missing data, and that came in very handy when people developed these algorithms for doing, voting among ensembles of models. But that's getting a little ahead of our story. Any questions about this? So notice that, we saw the basic algorithm, and then we saw a bunch of extensions of it, each of which is fairly straightforward, right? So we haven't seen anything really difficult or complicated to implement yet, but now we actually are beginning to have an algorithm that, you can throw real world data at it, and it might do okay. Okay. There is one huge issue that we haven't dealt with yet, which is overfitting, and we will talk, at length about that after the break. Okay. So it's 7:52. Let's start again at 8:02.